Hello, everyone. Hope everyone is joining us right now. In behalf of myself, Dr. Elwi from Egypt and Endostar, giving you today's this webinar. Hope you enjoy it and hope the voice is good. Anya, hope, and Anita, hope you're hearing everything is all right. The voice is okay. Let's start. My name is Dr. Elwi. This is my second time with you in Endo Coffee in the second version. Hope you will enjoy it. We will speak about the metallurgical point of view in nickel titanium from our clinical point of view and my cases and work. Let's start our presentation. First of all, I want to thank Endostar for this good chance to speak with you, to share our knowledge during this hard times. I feel it's getting better nowadays and everything is getting better, and I hope every one of you is safe. Our subject today as you know, I have been working with Endostar for more than 2 years now. Not working with them, but testing their files. I have my page, Timeless Endodontics. I hope you can visit and check my cases and my mini lectures on the page. Our title today is Metallurgy in Root Canal Treatment from the Clinical Approach, which means is our purpose from our webinar today is relevant for clinical endodontics. How come we can connect understanding the dental material with our practice or our daily practice in root canal treatment? As you know, we have a lot of variable instruments in the market from all vendors, all countries, all manufacturers, and as clinicians, we need to understand the different way of manufacturing for better use during endodontic treatment. So combination of files or even using single brand cannot be applicable in all your cases. So if you understand how they made or how they behave inside your root canal system, you can get yourself better and faster results. As a beginning, why we changed from stainless steel to nickel titanium alloy. First of all, nickel titanium alloys are one, as written in the presentation, are one of the several shape memory alloys in the market, but they have the most important practical application in dentistry or medical field as a whole, as biocompatibility with our bodies, corrosion resistant, non-magnetic reaction, and the most two important points that we will speak about them today are super elasticity and shape memory effect. Some people confuse the SE with the SME, or super elasticity, which is pseudo elasticity, with the shape memory effect. In case if you are undergraduate or postgrad, even myself, sometimes you can get confused by the two names. We will focus on them so you can understand how you can get the benefits of these 2 points in your treatment. Nickel titanium alloy, as an alloy itself, it's combined by nickel and titanium. By weight, 56% for the nickel and 44% for the titanium. We can say it's nearly 1-to-1 atomic ratio, equiatomic, but we have to know also that this percentage is sometimes changed by manufacturer to get different behavior of the alloy. according to application that it's used in. But mainly in root canal files, they have this ratio. Sometimes they add additives, sometimes they change the percentage to have slight change of the behavior of the wire itself. But to be more clear, this equiatomic nickel titanium have two phases. Okay, we have same percentage, same everything. We will standardize it. So we have 56% weight of nickel and 44 in titanium. But there's two phases, which is the austenitic and martensitic phases. The austenitic, we have to focus starting from this point. We call it the parent phase or high temperature phase, which have a cubical crystal structure. But the martensitic, it's present in a lower temperature phase, like in case of E3 Azure, when you make the file and produce it, it's near body temperature, it's present in this phase. This characteristics of superelasticity and shape memory will be present in both phases, only in the martensitic. But in austenitic, it's only a superelasticity or pseudo-elasticity. Okay? To be more clear, I will speak about it in the next slide, which is some people when we will see this this graph, we will say it's very complicated, but I will take my time to illustrate it for you by giving example. It will take us time, but it's very important to understand this graph. If you understand this graph, you will understand how the E3 file or any rotary file behave inside the canal. Okay, we have here stress and strain curve for the austenitic phase. Here, when we start in this point, is the martensitic phase. And also there's a stress and strain curve. The first point we can see in this graph that the martensitic phase can tolerate double the stress and strain, and sometimes more or a little bit less. It's not cannot be calculated because there's a different phase transformation, but still have more stress and strain toleration, more the austenitic. But if we start from this point, which is the martensitic point, the file can undergo deformation within the elastic point till reach here where point for plastic deformation. But in austenitic, you have one point and we can go to plastic deformation, which means file fracture. That's why martensitic files has been produced, not only to pre-curve the file or unaccessible areas to pre-curve it so you can insert it inside the canal. No, only also to take more maneuvers, more curves inside the canal. So here you have austenitic phase wire under heat process. It transfer, we have here AS and AF. This will return back again when we come back from here to back here. But we have here martensitic and start and martensitic finish, which is all the matrix of the alloy, mainly martensitic phase. So when we produce a file from austenitic parent phase and it's stable on the martensitic phase, and you go and use it inside your tooth, it will undergo deformation. Martensitic already as a matrix, it's a twinned face. So it will go under deformation to detwinned, they call it detwinned phase. So in this case, the file take more force and more deformation and still no fracture. But when you heat back again the file, which happened when we can see it in the manufacturer, sometimes you do it by lighter. But for us, when you sterilize the file, it will return back to austenitic phase, regain back its shape, and the D-twin come back to austenitic. Then after cooling in body temperature on room temperature, it will return back to martensitic phase when we can use it back again after sterilization, and it's still stable, but still can go under curvatures, under deep canals, under calcification. So whenever there is loading, it can take all this load, and in the same time it can deformed without fracture, can take more cyclic fatigue, can take more torsional fatigue without separation. I hope you understand this curve. We will go to the next slide. As you see here, to make it more simple, we have the austenitic wires, which cooled will give us the twinned martensite. After deformation during our work, it will be a D-twinned martensite, or deformed martensite, or deformed file, okay? But still the matrix is mainly martensitic nickel titanium, not austenitic. When sterilized, here, come back to austenitic. When you take it back out from the autoclave, cooling near to the body temperature, and when I say here, near to the body temperature, I mean the A3 Azure. Some brands and some other files doing another steps or heat treatment, which I will speak about it later today, that will make this temperature different, which give more phases, more different, we can say more different families from the nickel titanium. They all nickel titanium, but the difference is in the matrix is much different. I hope we pass this part for good, but here I will share with you one experiment I did myself, okay? As you see in the picture, this file is completely austenitic matrix at room temperature, which have only super elasticity or pseudo elasticity, which means you cannot pre-curve inside the canal. So I did here a reverse treatment, severe cooling by temperature minus 100 degrees. I used the Endo ice for a specific time. I pre-curve the file. It retain the shape for a time. When the temperature increased back again, the file returned back to its original shape. But in the same time, I cannot pre-curve it one more time. So what happened here is that due to severe cooling that I did in this area, I gained some martensitic matrix inside the austenitic or nickel titanium wire, but only for a while, because this file is mainly austenitic 100%. But in this picture, same file, I did increase in the temperature. If you want me to be specific, the austenitic phase is present at 1600 Fahrenheit, and martensitic start from 400 Fahrenheit. You can change this temperature so you can get different breeds or different families from the nickel titanium. To remember with me, I want you to remember most of the brands in the market, you have this color, you have some brands have this color, some brand have this color, some like E3 Azura have the blue color. So in this picture, I made a different heat treatment all over the austenitic wire. And I didn't touch the file. And as you can see, you have a different phase transformation. As if you want to see in the next slide, I curved the file, and you can curve it here and keep the shape, gain the super elasticity, and in the same time shape memory. So if you sterilize it back again, it will return back it doesn't mean that this file now turned to be martensite, but this is example how manufacturer can subject the original austenitic parent centered cubic shape to temperature or different temperature or heat treatment process, so can gain different kind of files in the market. In case, as you can see, this one is the blue color. So changing in the heat treatment process can give you different mechanical and metallurgical properties to your nickel titanium wires. So what I can gain from all this data, to simplify it a little bit, super elasticity is mainly a mechanical effect, but shape memory is temperature effect. What it means by these points, when your file is super elastic, it's called also in the same time pseudo elasticity. This pseudo elasticity means when you remove the force from the file, it wants to return back originally to the original shape, not by temperature, not by anything. So this properties make the file a little bit tough, strong, but in the same time you cannot use it in all the cases. But the shape memory you can pre-curve and make it according to your case. To show it more for you, I made this picture. No, not this one, the one next to it. Here's the austenitic file. When you make a pressure on it, you can curve it, but when you remove the load, it will return back like this. But martensitic nickel titanium, when you curve it and you remove the load, it will give you the shape. Sometimes when you get the file out of the canal, you can have a 3D image of your canal inside your mind. So that's very good about the E3 Azura. When I do a case and it's severely curved, I remove the file slowly so I can imagine how the file goes through the canal. In the next picture, as you can see here, this is the austenitic file. It's straight, but when you curve it, only you need force to curve it. But after you remove the force, it will return back like this. But in case of heat-treated files, when you remove the load, it will keep the shape, like in this picture. I curved the file on the block, and when I remove the force, it keeps the shape. So this point have a lot of application in our practice. Some people say, no, I use it only to pre-curve the file. No, we will speak about it today. You will get a lot of benefits. Nearly, I use it now maybe in 70% of my cases without any kind of manual files. Okay. Now, I will try to go a little bit slower so I can speak in about some cases and next. Nickel titanium alloy, as I have said before in this picture, if you remember, I want to return back to it. Different heat treatment, different nickel to titanium proportion give you different color, different mechanical properties that impact your work. Only change in temperature or cooling process during production can give a tremendous change in the mechanical properties, not only regarding the design and the taper, but only changing temperature by small difference give new generations of files, which is available in the market. As we will speak right now, the old conventional nickel titanium, which is austenitic, he have only the properties of being super elastic. But our phase, which it's a phase between the martensitic and austenitic, it's super elastic, and they have been able to make the file to be produced by twisting, not by grinding. Many researchers say that the twisted files is keeping the integrity of nickel titanium wire and reduce the micro cracks in the file so it can resist the cyclic fatigue. But it's not applicable on all of the cases, but this is one of the generation. We have also the M wire, which is austenitic, but in the heat treatment process, there's a small amount of R phase and martensitic phase, which have super elasticity and two-stage stress-induced transformation through the R phase, which means that the file can take more curves and can go inside the canals, but still not up to the level of the completely heat-treated file. Next stage, the controlled memory wire, which is martensitic, but have a less amount of austenitic and R phase. It's files that you can pre-curve, but still not to double curve canal, but it can be used, and it's highly cutting, have a high cutting efficiency, high quality files, but it's only one of the generation. Max wire